we're going to be talking about roots and radical expressions. So here, a is the nth root. Now, n would be our index. We have our radical sign here, and then the number underneath the radical sign is our radicand. So once we take the nth root, we get a value a. So nth root means how many times you can multiply a number times itself to get another value. So for example, let's look at the number 3. Let's say I do 3 times 3 times 3. Well, we know that should be 27. Therefore, I can write that as 3 cubed, which equals 27. So the cube root of 27 is going to be the value 3, because the cube root and the cube here will cancel each other out, and I just get 3 as the cube root of 27. All right, so 3 is the third root of 27. So depending on if my index is odd or even, I will have a different amount of roots. So if n is odd, I will only have one real nth root of b. So if it's a cube root or a fifth root or a seventh root or anything that's odd, I will only have one real root. Now, if n is even and the number underneath is positive, then I will have 2 real nth roots. Now, if b underneath is negative, I will have no real nth roots of b. We will either have imaginary roots or it will not be possible to find a root. When defining what a principal root is, we have to break it into 2 cases, when our index is even and when our index is odd. Now, when we have an even index, we can actually have a positive or negative root. Now, the positive root is called the principal root. So for example, let's say I want to take the square root of 100. Well, there's actually 2 numbers that can give me the square root of 100, because 10 times 10 gives me 100, and negative 10 times negative 10 gives me 100. But the principal root, which is what we often think of, is just 10. Now, if my index is odd, we only ever have one real root. So for example, let's say I want to take the cube root of 27. Well, the only value that will give me that is positive 3. But let's say I want the cube root of negative 27. The only value that will give me that is negative 3. So for odd indices, the principal root is always going to be that one real root. Now, it's common to say that if the radicand is positive, then the principal root will be positive. If the radicand is negative, then the principal root will be negative, but that is only for odd indices. Here's a more formal definition of the principal root. So whenever your indice is odd, then you just take the value a whenever it's raised to the nth power. But if your indice is even, you have to take the absolute value once it comes out of the radical. So for example, if I have the square root of negative 3 squared, well, I would take out the negative 3, but then I would have to take the absolute value, so the principal root would actually just be positive 3. But if I had the cube root of negative 2 cubed, then I would just take the value negative 2. So for odd powers, you're allowed to have a negative principal root as long as the radicand is negative. For an even power, your principal root is always positive. To simplify a radical, you look at the index, and that's how many of that particular number or variable you need in order for it to come out of the radical. So whenever I have a square root, the index is 2. We don't normally write the index of 2. It's assumed that it's there, which means I need 2 of every number or variable for it to come out of the radical. So I can rewrite this as 5 times 5, x times x, and then a y. Therefore, I have 2 5s, so one of the 5s will hop out. I have 2 x's, one of the x's will hop out. So this will simplify to 5x square root of y. Now, when you're dealing with cube root, the exact same thing applies, except for now I need 3 of every number. So I can rewrite 8 as 2 times 2 times 2. X squared is x times x, y cubed is y times y times y. So anything that appears 3 times will hop out. So a 2 will hop out and a y will hop out. So I'm going to be left with 2y cube root, and then my x squareds stay inside because they don't have enough to come out of the radical. So this rule applies for any nth root. If you're taking a fourth root, you need 4 of everything in order to have one of them come out. Fifth root, you need 5 of that particular thing to have one of them come out of the radical. When simplifying radicals, you want to look at the index and make sure that you have 3 of a number or 3 of a variable for it to come out of the radical. Now first we're going to look at the number, and we're going to do the prime factorization of this number, and then we're going to focus on the negative in just a second. So 125 is 5 and 25, 25 is 5 and 5. So I can rewrite this, make sure you don't forget your index here, as negative 5 times negative 5 times negative 5, or simply negative 5 cubed. Therefore, the negative 5 will hop out, and I'll just be left with negative 5. So anytime your indice is odd and your radicand is negative, your principal root will also be negative. Now down here, we're going to use our same properties that we did with square roots with the cube roots, and it works for any nth root. We can break this up. So we are going to continue to find the prime factorization, also looking for perfect cubes. So 128, well, that breaks down into 8 and 16. 16 is 8 and 2. And remember, 8 is a perfect cube because it's 2 times 2 times 2. So that means I have 2 2's that will hop out. Now 343 is 7 and 49. 49 is 7 and 7. I have 3 7's, which means 1 7 will hop out. Now when this 2 hops out and this 2 hops out, they are going to multiply together. So I'll be left with 4 cube root. Don't forget to put your indice here. And then what's left is this lonely 2 over here. And on the bottom, since I have a 7 and nothing else left, I'm just left with 7. Now if this 4 and this 7 could simplify, we would, but they can't. So my final answer is that. When simplifying a radical with variables underneath, you still need to check the index, and we need 3 of that variable to appear in order for it to come out. So I can rewrite this as x times x times x times x times x, or x cubed times x squared. So anytime I see 3 x's, that will hop out, or anytime I see something to the third power, that will hop out. Either way, we will reduce to x times the cube root of x squared. Now in this second example here, in example D, we have a negative underneath the radical when we have a even index. Now, the only time that that is allowed is when we have an index of 2 or a square root. And when you have a negative underneath the square root, we know that gives an imaginary answer. But for any other even index, this is not possible. There is no number I can multiply times itself 4 times to give me a negative 1. If this first example here could simplify under the radical, we would, but it does not simplify. So we're going to break it up. So I'm going to be looking for perfect cubes in 16. Well, 16 is 2 times 8, and we know 8 is a perfect cube. So we are going to take out a 2 and be left with a 2 under the radical. Don't forget your index. Now on the bottom, 81. 81 is 9 times 9. 9 is 3 times 3. So I'm going to get 4 3's. So 3 of those will give me 1 3 on the outside, and I'll be left with a 3 on the inside. Now if things could simplify, we would, but they don't, so this is going to be my final answer. Now down here, my index is 5, which means I'm looking for groups of 5. Well, here the p is already to the 5th power, so the p will hop out, and I need to rewrite q so that I have groups of 5. So I'm going to have p to the 5th, q to the 5th, and how many are left over? There's 2 once I separate them. So I'm going to have the p come out since it's to the 5th power. The q will come out since it's to the 5th power. So I have pq, 5th root, don't forget your index, q squared. So this is going to be my final answer. Most common mistake, people forget to write their index, so make sure that you rewrite the final answer with the index you started with. This chart will come in handy whenever you are searching for perfect cubes or perfect fourth roots. For these examples, I want you to simplify all the radicals. You can assume that all of the variables are positive. Please write your answers in your notes.